Hello everyone. Today I want to share our recent work called PBE-CC, Congestion Control via Endpoint-Centric Physical Layer Capacity Measurements. I'm Yasheng Xie from Princeton University. This work is about congestion control. If we model the TCP connection as a pipe, then the size of the pipe is determined by the bottleneck capacity. The design goal of modern congestion control algorithm is to match the sending rate to the bottleneck capacity. This job becomes challenging in cellular network. Most of the time, cellular wireless last hop is the bottleneck, and its capacity varies significantly and rapidly. Before explaining why it varies, let's look at two important parameters that determines the capacity. The first one is the allocated bandwidth. Both 4G and 5G adopts OFDMA, which divides the time into subframe and frequency into small blocks called physical resource block. Base station has a resource allocation algorithm that allocates different number of PRBs to different users. The allocation varies from subframe to subframe. Another important parameter is the wireless channel quality, which determines how many bits can be carried inside one PRB. Base station has a readaptation algorithms to select different physical layer configuration like MCS index for different user. These two parameters determine the capacity, and these two parameters varies in a practical cellular network. We all know that a typical base station can serve hundreds of users simultaneously, and the data usage pattern of different users is highly dynamic. As a result, the resource allocation is also highly dynamic in cellular network. What's more, the channel quality between the base station and the mobile endpoint varies with the mobility of the user, and user mobility is very common in cellular network. What's more is the carrier aggregation. Both 4G and 5G supports carrier aggregation, which enable one user talk to multiple cell towers simultaneously. As a result, the user experiences the dynamics of all of its aggregated cells. So purely relying on end-to-end metric like RTT, packet loss, packet time steps cannot track such a fast varying capacity. It's challenging, but it is possible. We observe that the cellular network has a dedicated control channel to deliver all the information we have mentioned, like the resource allocation results, the carrier aggregation results, and the physical layer configurations to the mobile user. Most importantly, the control channel is not encrypted, which means a mobile user can decode every control message sent over this channel. We therefore observe opportunity that if we enable the mobile endpoint to snoop on the cell towers, then the congestion control endpoint can know the state immediately without any infrastructural changes required. Based on our observation, we propose PBE. The architecture is given in this figure. The server sends data to the mobile client, and the mobile client estimates the capacity of the cellular link based on the physical control message and feed it back to the server. Server extracts the feedback and matches its sending rate to the estimated capacity. So there is a very important question to be answered. How does the mobile client estimate and track the capacity? I won't cover the technical details of the algorithm, but I will use two examples to show the basic idea. In the first example, I will show how PBE tracks the capacity under competing traffic. First of all, without any competing traffic, one user can take all the bandwidth. When competing traffic comes, the base station allocates resource blocks to the competing traffic. So user 1 in this case observe less PRB allocated for itself, so it can inform the its sender to lower down its sending rate to adapt to the competing traffic. Similar for the 3-user case. In the second example, I will show how PBE tracks idle bandwidth. Idle bandwidth appears when a user finishes its transmission. For example, in this case, user 3 finishes its transmission in the 3rd subframe, so idle bandwidth appears in the 4th subframe. Then user 1 and user 2 immediately detect such idle bandwidth by looking at the control message and then inform their senders to increasing the sending rate and then take the idle bandwidth fairly. Except the capacity estimation, we have many other issues. For example, we have the bottleneck alternation issue. The location of the bottleneck may alternate between the internet link and the cellular link. PBE only estimates the capacity of the cellular link, so we need to take different actions when the bottleneck is at different location. We also need to detect where the bottleneck is. We have another issue is that based on the decoded control message, we actually get the physical layer data rate, but the server needs the transport layer data rate so that it can set its sending rate. Therefore, we need to perform a cross-layer bit rate translation. Then I want to briefly share our experimental results. In this experiment, we test with static users, and we compare PBE with 7 different algorithms. In this 4 figure shows the results in 4 different scenarios: idle hours, busy hours, 1, 2, 3 aggregated cells. We plot the throughput and delay in one figure. The right upper corner is the best. So you can see PBE achieves lower delay and higher throughput than all 7 algorithms. Next, I want to answer some questions raised by the reviewers. The first question is about the power consumption. The reviewer asked, does PBE need to keep the radio on for extra time to decode the control message? Our answer is that PBE doesn't keep the radio on for any extra time. Specifically, let's look at the structure of the LTE subframes, which is divided into a control channel and a data channel. Every user has to decode the control channel first before decoding the data channel. The reason is to get the number of allocated PRBs for itself. Even though the base station may allocate 0 PRB for one user in any subframe, but the user has to keep the radio on to listen to the control channel of every subframe. So PBE doesn't keep the radio on for extra time. Another question is about triggering carrier aggregation. Our goal is to match the sending rate to the capacity so that we can minimize the packet buffering in the network. So the review asks, how can you trigger the carrier aggregation without buffering data at the base station? Indeed, we have an example in our paper showing that when a user triggers packet buffering at one base station, the cellular network observes that and activates multiple cells to deliver data to this user. But we want to emphasize that buffered packet at the base station is not the prerequisite for triggering carrier aggregation. As long as you are using a large number of bandwidths, the cellular network will automatically detect it and activate secondary cells for you. The last question is about the malicious user behavior. What if a malicious user always feeds back a high data rate to the server? If we allow this to happen, then the server may send to this user with a very large data rate. Our answer to this question is that we can easily extend PBE to detect such user. To detect such user, we need a throughput measurement. For example, BBI implements a server-side throughput measurement scheme. And then we compare the feedback with the achieved throughput and identify a user which consistently report higher data rate, report capacity estimation that is higher than the achieved throughput as a malicious user, since the capacity report from this user is never achievable. So thanks for listening to the talk. I'm glad to answer any questions you have.
Perfect. Thanks, Don. So I'm going to again read out a few questions, starting with the first question is from Lloyd Brown. Lloyd is curious if scavengers would result in lowering of network usage when there is a competing L2 user. And if not, then what is the incentive for a user to adopt scavenger transport when competing with hosts it doesn't care about?
Yep, sure. Thanks for the question. And so as long as there are competing flows and also the buffer or the bottleneck utilization is approaching full, so then we expect the scavenger to back off. And then regarding the latter part of the problem, that's actually a very good question. And we explained that in our 20-minute video using a motivation page, like who will use the scavenger. So yes, when there is multiple flows or multiple applications run by the same user on the end host, then it makes sense that user may want just some background applications to back off for higher applications quality for foreground applications. And on the other hand, when users only have one flow, and in that case, the incentives for this user to back off is from, for example, the equipment manufacturer and also the service provider, like Google in my example, that provides multiple services like Google Drive and YouTube. So in that case, the bottom line is that changing the priority of one flow for one user from a primary to scavenger should not impact this user's quality of experience. And on the other hand, by doing that, because people are sharing the internet with kind of limited bandwidth resources, so that may enable other competing users elsewhere in the world enjoy better QoE. So for example, service provider, that means possibly more revenue and more satisfactory user experience. So that's incentives for this case.
Perfect. So there are some constructive feedback coming from Lars and Anna that it would be good to look at LED BAT++, sure. which is perhaps a good comparison point. But I'm going to stick with questions. So one of the interesting questions is, where should PCC Proteus be deployed? Is it inside smartphones? Is it inside home routers? Or what do you see as the primary or interesting deployment scenarios?
Yep, thanks. So that's a pretty practical question. And similar to all previous PCC works, we only expect sender side changes. So in many cases, that is the server side or service provider side. And in that case, like big service providers like Google and other companies like Facebook, they can deploy this Proteus architecture, and then they knows what's the corresponding requirements for different applications, like the bit rates for YouTube and latency responsiveness for Facebook posts. And then they can adjust the relative priority accordingly. And then besides that, there is those cases that users use uplink and need to determine the priorities by themselves. So in that cases, we think first, users are still using the service, so the priority can still be communicated with the server side. And the other possibility is just let the user deploy it, but that will induce higher adaptation overhead. So we do not consider that path right now, but that's also a available choice.
Thank you. That was a great talk. We have a few questions trickling in, so I'll sort of start asking those right away. So the first question is there a mechanism to determine the fair share of the idle bandwidth?
Yes, because PBE can detect how many active users is currently using the bandwidth of the cell tower. So we can directly calculate the fair share of the idle bandwidth, and then each user will grab only its fair share portion of the idle bandwidth instead of grabbing all the idle bandwidth that appears.
Great, thanks. Okay, and then the next question is, So what is the delay between some sort of change in the physical condition to the endpoint receiving the control message? So what's the lag in the control messages?
I think for all LTE device tie into 1 millisecond subframes, so the delay is actually 1 millisecond because we can immediately detect the control message in this subframe. So the user can immediately know what's happening in the channel.
So, okay, so the next question is, I kind of had a similar question. So I'll sort of merge my own question with the question that appeared in Slack. So have you compared two schemes such as ABC, where the sort of the base station or the router sort of actively controls, this is when you have bandwidth, this is when you don't. So do you compare against such schemes? And
no, we didn't compare with, we didn't perform head-to-head comparison with ABC because ABC is actually, it requires the modification to the base station. We didn't have any modification to the base station. We only changed the client. So it's a client-side solution instead of the router-side solution. So we didn't compare. And because and also we conduct all of our experiments in a commercial LTE network. So we cannot change the base station also.
Okay, great. Okay, and then the related question is, do you think there are any overheads with like PBE-CC compared to schemes like ABC? So ABC, I agree, requires like base station changes, but are there like any other overheads that are introduced in this endpoint-based scheme?
Yes, we needed to decode some extra control message. So a typical legacy user only decodes the control message that is transmitted to itself. So it will discard all the other control message. So we need to decode some extra control message to get the full picture of the current bandwidth usage of the base station. So that's our.
Okay. And so the next question is, does PBE-CC need to modify the user's kernel to support control channel detection, or the control channel detection can be done using a non-intrusive plugin?
Yeah, we need to change the firmware of the mobile device.
Okay. And okay, so the last question is, what happens when the base stations start encrypting control data?
Yeah, of course, that became a problem if they began to encrypting the control data. But currently, as far as we know, like 4G and 5G, they didn't do it. So I think in the foreseeable future, it's still feasible.
Okay, great. So if there are any more questions, you can sort of continue posting them on Slack, and I'm sure Yasham will be happy to answer them on Slack. Yeah, thanks.
Yeah.
It was
Thank you.
It was great work. Yeah, it was fun listening to the talk. Thanks, Yasham.